is on oscillations and waves. You can see that there is a pendulum is oscillating. Okay, so we'll see many such oscillations in our very daily life. So we will try to understand the physics of these oscillations. So in this chapter, according to the V2 syllabus, the module 1 is on free oscillations and the damped and forced oscillations. This is the first chapter. It's split into two halves, and the second chapter is the shock waves. This is the second chapter in the module 1. Here the oscillations and the shock waves are slightly different kinds of the topics. Therefore, it is split into two chapters. We'll understand these things when we go into the syllabus as and when. Okay. Right now, don't worry. I'm just displaying the today's class along with the syllabus of the module 1. So in this class, you'll be able to understand these other things. Types of motion. Already know that what do you mean by motion. So in motion, there is some particle or an object that traverses or travels from one point to the other point. So it is a kind of displacement of the particle from one point to the other point. It is such motions are generally termed as translational motions. And there are some cases where the particle, an object, will kept on making periodic movements. I have seen in one of the diagram, the very first slide, there was a pendulum that is swinging about a point. So it is a kind of oscillatory motion as well as periodic. What in the periodic motion? There is something that goes, that changes the periodically. Maybe it is amplitude, frequency, whatever it is. So the particle that changes periodically with the time. Okay. So such motions are periodic. There is a slight difference between periodic and oscillatory. We'll be able to understand in the next coming slides. Okay, I have given here one of the example for the oscillatory motion. That is the motion of a simple pendulum. One more example is given as the vibration of the spring. You just imagine the motion of the pendulum and you imagine the vibration of the spring, how it does goes through. So they are the examples for the oscillatory motions. So in this class you are going to understand this simple harmonic motion associated with the oscillatory motions. So oscillatory motions are nothing but the simple harmonic motion, and you will see that the energy is conserved in the simple harmonic motion. Similarly, therefore, and again, the springs, the vibration of the spring also satisfied by the simple harmonic, the conditions of the simple harmonic motion. Probably at the end of today's session, you'll be able to understand what are the characteristics and properties associated with the simple harmonic motion. And the differences between the periodic and oscillatory will be understood. At the end, ultimately, if the time permits, I hope we'll be able to complete the differential equation for the simple harmonic motion. That's the expression. We are going to get the expression for the differential equation for simple harmonic motion. So these are the kinds of motion we observe in nature most of the time, isn't it? See here, there are 6 kinds of diagrams with the kinds of motion, and the first column you will see that vibratory motion and oscillatory motion. The second column is the linear motion. It's mentioned as linear motion, circular motion, and the third column is curvilinear motion and rotatory motion. It is here actually speaking, there are 2 kinds of motion. In general, there will be 2 kinds of motion. One is translatory motion and other one is the oscillatory or the periodic motion. Here, though the nomenclature is slightly different, that is to explicitly show that the kinds of motion. Okay, but in general, there will be two motions. Look at this man here. He is pushing the load. You see, this man is pushing the load. What happens after he push the load? It may be displaced to some point to the left. Okay, so he is changing the position of the particle or the block here. And in the second, in this particular diagram, the boy is playing the football. So when he kick the ball, it goes curvilinearly, somewhere it stops. And you see in these two cases, the particle has displaced from one point to the other. So we can say that this kind of motion is the translatory motion. Coming to this fan, see when you switch on the fan, the wings of the fan keeps rotating about the axis. Okay, so and when you switch on the fan, you cannot expect the wings to come to the same position. So this wing has been displaced somewhere here, or it may move this side or so. Likewise, there will be a motion of the particle, but not specified to its original. In all these three cases, you will not see that the particle is going to come into the same place. It is not possible. So these are called the translatory motions. And here the settlement goes round and round. So you cannot expect to come to the same point at the in one complete oscillation. It's not so. In each rotation, the satellite will not come to the same point. It is going in all 360 degrees. So you cannot take this as the translatory motion. Coming to this first case here, see this is it is mentioned as vibratory motion. We have already seen that the string of a VR guitar, when struck the string, it this oscillates, vibrates, and after some time it will come to its original state, isn't it? So the particle is coming back to its original state, original position. And here, when you swing a pendulum, see this goes to left and right, it makes a to and fro motion about the point O here. Here I call this O as the equilibrium position or the rest position. This O is called as the equilibrium position or the rest position, because when there is no load, this pendulum remains in this position O. Because of gravity, it is remain stationary at the point O. When you allow this oscillator spring to vibrate, push, when you push this spring, it keeps on moving to the left and right of the O. That is the rest position, and ultimately it will come to and it stops at the this mean position. So in these two, that is in vibratory motion and in the oscillatory motion, you have seen that the particle will come to its mean position or the rest position after some time. In all other these cases, whether linear, curvilinear, rotatory, whatever it is, on the right side, in all these kinds of motion, the particle may not be coming and coming to the rest position. So that is not possible. So such motions are called here they are linear, and the left side is called the oscillatory or the periodic motions. Okay, I think so many students are waiting. I'll just go back and check and I admit them and come back to you. Okay. See, we have seen that in the diagram, the previous slide, the motion of the things can be broadly classified into two kinds according to whether the moving body travels from one place to another or stays near one fixed position. So the travels from one place to another is translatory motion. This is the translatory motion, and one that is fixed at the rest position. See here the pendulum is moving across. That is to and fro motion about the rest position. So that is the circular motion. So coming to the definition, I already explained the translation of the linear motion. Just to show the comparison between the translatory and the oscillatory, I've just included this diagram. Don't worry, right now you already understood. So in translatory motion, I can give some more examples of the snooker ball, a sliding snooker ball. When you hit the snooker ball with a striker, it goes at remains occupies some other position, and you see that I say, for example, if you look at the wheel of a car, see that car wheel, it need not has to come to the if you mark some point on the on the wheel of the car, let us say you mark some point on the wheel of the car, and when it runs through a certain distance, you cannot expect the car to have the same position. So, when you look at the waves, ocean waves rolling towards the beach, they are it is displaced. So it is displaced from one part to the other. So they are the few examples for the translation motion. So you understood the differences between the translation and the vibratory or oscillatory motion, and read off the things here. These are the look at these are the, again some more examples. Here imagine observe that in the park the kids play the swing. No, here the kids play the swing. They are the examples for the oscillatory motion. The motions in which the things or bodies that stay at one place, or it makes to and fro motion about a fixed point. Okay, these are the oscillatory motion. I hope you understood the meaning of the translatory motion and the oscillatory motion by this time, and given examples. So I was telling you that the oscillatory motions are periodic motion, isn't it? So a periodic motion is an oscillatory motion. That is a very oscillatory motions are periodic, but periodic motions cannot be oscillatory. Okay, so one of the best example it is already given, a pendulum that swings about the equilibrium position, that is to and fro motion, is going to exhibit a behavior of a sinusoidal law. I'll show you. I'll use some screen here to show you. See here, this is imagine this is the pendulum. When this is allowed to move, swings on either side. This is probably the extreme end. So, swings like this. Okay. So now, if you call this plus x, and this is minus x, so it goes like that, and ultimately it will stop. So now I can draw this diagram in this way. I am drawing with decreased amplitude because over the time it decreases in the amplitude. If the medium is free from any other resistive medium, it may go with the same amplitude. We can see that later on. So I call this as displacement. What is x here? is displacement. We call this as displacement. And do this with respect to time t. So this may be the maximum amplitude. So now here in this you can express the displacement x is equal to some amplitude sine of, it is just like, looks like some sine wave, no? Sine of omega t plus delta. We call this delta, I can put as the phase. Here it is taken only one wave, so we cannot expect the phase right now. That is 0. Otherwise, it is like otherwise, and that thing is not legible here because I'm using some electronic equipment. It's not so legible, so please bear. So now, 1 minute. Okay. So I rewrite this x. Oh, and rewrite it here. I can write x is equal to some a amplitude sine of omega t. This is the expression with respect to sinusoidal wave. Okay, so this is the displacement of the periodic. Later on we call this as simple harmonic motion. Okay. Okay. So you have seen that the pendulum swings to the to and fro motion about the fixed point, and that is that obeys the sinusoidal law. You have seen that here. It obeys the sinusoidal law. I'll come to this diagram after some time. Here you see that this is the pendulum, and it is swinging. You will see written this mg sin theta, that is called the restoring force, and there is a force due to the weight mg, that is mg cos theta. We'll understand this later. Right now, we want to see that this is pendulum, whose length is L, the string length is L, theta is the angular displacement, and there are two forces. One is the vertical component, that is mg cos theta, and the horizontal component is mg sin theta. This mg sin theta is defined as the restoring force. We'll see that. So now we are trying to understand the simple harmonic motion with respect to. Yeah. Yes.
Sir, here is waiting. Let them in, sir. Is waiting. Meeting. Let them in, sir.
Because if I have to end the show and get us to something. That's why I asked you to. Okay. I'll come back to this. Okay. we are trying to understand the simple harmonic motion. Here in simple harmonic motion, the okay. So you have understood that all periodic motions cannot be simple harmonic motion. Then what do you mean by simple harmonic motion? The example is given here, the oscillations of a simple harmonic motion. I'll explain this. Okay. So we have seen that the example for simple harmonic motion, that is example simple pendulum. So the example I gave it is this one simple pendulum. See, bear with because I have to use the gadget here every time I'm changing over to this particular screen, and I have to select the pen eraser, etc., all those things. So it may take little patience from your side also. Okay. So now this is pendulum, that is goes this way. Imagine this is somewhere at some point of time. This is the maximum. So it is moving to the extreme end, means it is moving this direction. So it stops somewhere, means velocity is 0. And the kinetic energy, it stopped now, therefore kinetic energy is 0 here. And you know that our total energy is potential and kinetic, isn't it? So total energy, that is E, is kinetic plus potential. So now here this particular case here at this point, velocity is 0, means kinetic energy 0, potential energy is maximum, isn't it? It will be maximum. So when it is coming, let us say it is coming this direction. When here at this extreme end, when the velocity is 0, means kinetic energy is 0, potential energy is maximum. This is maximum. What about the force? It is going to stop here. The force, because the particle is going to stop here, and thereafter it is coming back. Therefore, it comes because of the restoring force, that is negative here at maximum. Okay, so because it is coming back, and at this point it shoots to the other side. So velocity here it is shooting, so velocity becomes maximum, and kinetic energy becomes maximum. Potential energy is minimum. So between this extreme end, this is the extreme end, to this point of equilibrium position or the rest position, particle has been traveled, isn't it? So the kinetic energy is 0 here, and the potential energy is maximum. So kinetic energy is converted to potential energy, and when it goes to this point again, because the velocity is 0, kinetic energy is 0, and potential is maximum. So you will see that there is continuous conversion of kinetic to potential. You see here the continuous conversion of potential to kinetic energy and kinetic energy to potential energy. So energy gets conserved here. Energy conserved, isn't it? Energy is conserved if suppose this medium is occupied by a resistive medium, maybe it is air or some other oil, any medium. If there are resistive medium, the amplitude slowly decreases. Otherwise, the amplitude continuously keeps constant, and the energy is continuously converting to one form to the other. That is kinetic to potential, potential to kinetic to potential, and so on. So now the bob is look at this. The bob is coming towards the equilibrium position. When it's coming in this direction, it comes towards the equilibrium position. So it is making to and fro motion, making to and fro motion. Why this bob is swinging? That is because we call this as the restoring force. Bob makes a to and fro oscillation motion because of the so you can define the restoring force as it is the internal force developed by the body that works against the acceleration due to gravity here. Okay, so this F and Fr are opposite. F is the force due to acceleration due to gravity, and Fr is that is within the that is whatever the system develops an opposite force with respect to the force, the external force, that is called the restoring force. I'll give another example. For example, you take the spring. So there is no load right now. When you apply the load, it swings, so it has come down. This was the, and it goes up, like, isn't it? So now the energy is when it got extended, that is because of it, and when it is going back above, that is because of the kinetic energy. So kinetic and potential energy is changing over. Okay, so why this swing moves up and down? That is because of the restoring forces. So the restoring force that is developed within the system, that is always opposite to the applied force or the force due to acceleration due to gravity here. Okay, so restoring force, it is the force that is within the that develops within the body opposite to the external force. So F and Fr are opposite to each other. Okay, so now there is a restoring force is acting on the body. So now if I can use Newton's laws of motion here, for example, okay, here I'll write say this F is equal to ma. That is Newton's laws of motion. Okay, and every spring the force is we have already seen. I'll use again one more slide. Okay, so here this is the, I mark this as plus x, and this is minus x. Okay, so it is swinging, and this is, there is a restoring force, imagine Fr. So this Fr is restoring force is proportional to the displacement. Fr is proportional to this is the displacement x, starting from 0. So Fr is proportional to x, and this is directly proportional to a displacement. This Fr is opposite to the displacement. So restoring force is opposite to the and directly proportional to displacement. You see that here, here this Fr is 0, isn't it? I mean, Fr is maximum. Therefore, it is coming and here Fr becomes minimum here. Okay, there are some lines that come in between. Yeah. Can I draw this diagram once again? I think there are some lines that's introduced. I'll draw this. I'll draw this once again. So this is V is 0, velocity is 0, Fr is maximum here. Because restoring force is opposite to F now, this is because F is minus Fr. So this is maximum, therefore F is 0, this is 0. And here at this point, Fr is 0 because F is maximum, is 0. So, and this is the distance, this is the displacement, is starting from x here plus x. You see that here at this point x is maximum and you see x is maximum also. Isn't it? Here x is minimum. Therefore, Fr restoring force is proportional to x, and this is directed opposite in this direction, therefore it's negative. Fr is minus, and I take out this proportional constant as k and x. So this is the restoring force in terms of spring constant. What is that? K is the spring constant. Okay. So Fr is minus kx, proportional to the displacement. What is x here? X is displacement. This x is displacement. Okay, so restoring force is proportional to the displacement but acts opposite to the direction of motion. Okay. So now F is equal to ma, that is equal to minus kx, isn't it? F is kx. Now is another spring. So we know that F is equal to ma, that is from Newton's law. That is from Newton's law. It is from Newton's law. So this is Newton's law. And it is minus kx. So we say that this is within elastic limit. One minute. Okay. This is with respect. This is with okay. One minute, please. This is according to elasticity or Fuchs law. According to elasticity. now we have seen that F is equal to MA is equal to minus Kx. What is this A here? Don't confuse with amplitude. A is acceleration. Therefore, acceleration is equal to minus Kx by M. So, this is the acceleration in simple harmonic motion. Okay. So, you can define simple harmonic motion as it is the motion of the particle whose acceleration is proportional to displacement. You can also define as it is a simple harmonic motion where the acceleration of the body is proportional to the displacement, and it is opposite to the upward, opposite to the direction of motion. So acceleration is proportional to displacement. Okay, that's how we can define a simple harmonic motion in terms of acceleration also. So I understood now for a simple harmonic motion it is this should valid. Acceleration is proportional to the simple displacement. So you can define simple harmonic motion as a motion in which the acceleration of the body is directly proportional to the displacement, and it is always motion is always directed towards the main point at the equilibrium position. Okay, such a motion are the simple harmonic motion. So if you look at this, here is a periodic, as well as it has to satisfy the acceleration proportional to the displacement. We may not expect this similar acceleration proportional to displacement in any other periodic motion. So all simple harmonic motions, they are periodic as well as oscillatory. Remember, simple harmonic motions are periodic as well as oscillatory in nature. Okay. So understood the restoring force, and that is Fr equal to mg. I already explained this. So Fr, the restoring, this is that is proportional to minus x. Fr is equal to minus kx. Okay. This Fr is equal to minus x. Okay, they are opposite. This is the vector, they are opposite in nature. Okay. Here Fr, because of Fr, the bob is making to and fro motion. The bob makes to and fro motion. To and fro motion. This is Fr. This is Fr. This is Fr. Okay. So we already explained you that the conservation of energy, that kinetic energy to potential and potential into kinetic energy. If you plot the kinetic and potential energy, it looks like this way. Say this is I use the pendulum every time. V is 0, kinetic energy is 0, minimum, potential energy is maximum. Here kinetic energy is maximum, potential energy is minimum. So if you plot the kinetic energy and potential energies, see here look at this diagram. I'll explain what is this. See, when this is with respect to the x displacement 0 plus x minus x here. So this is plus x and this is minus x 0. You look at this kinetic energy is 0 at plus x. So this is potential energy. Alright. So kinetic energy is maximum where at x equal to 0. We'll get another curve. This is for kinetic energy. This is for potential energy. See, the potential energy is as a function of this displacement, so it is maximum at x here, and it is a minimum at this point. So it's minimum at this point. Okay. So and it is maximum. The other experiment here potential energy is maximum, so it is maximum here. Okay. And similarly, the kinetic energy is minimum at maximum here. Kinetic energy is minimum at here, so plus x. So it is minimum here. So kinetic energy is minimum, and it is minimum. That's the answer. Okay. So the kinetic energy is converted to potential, and potential is converted to kinetic energy. When the flying bob, when comes to the mean position here, when comes to this position, since the force is 0, according to Newton's laws of motion, that is body or a particle continues to be in the state of rest or motion, isn't it? According to Newton's law, a particle continues to be in the state of rest or motion because of the inertia. So it shoots to the other side because of inertia. Okay, inertia in the body. Okay. So now, coming to, we already explained the conservation of energy. When the bob is displaced from the equilibrium position, the gravitation force gives rise to the vertical component. You have seen that. And the horizontal component is represents the restoring force, and this restoring force is mg sin theta if you do the trigonometry. And when the bob reaches the midpoint, restoring force vanishes, isn't it? Because Fr is 0, and because the F is equal to ma, Newton's laws of motion, the acceleration shoots the that is what takes the swinging of the pendulum to the other side. The inertia is a property causes the bob to overshoot the equilibrium position, and the motion continues. Once again, the restoring forces come into action, but the change in direction, isn't it? So the restoring force is maximum at the extreme position of the bob, and stops at stop the bob to pull back towards the equilibrium position. The result is continuing oscillatory motion of the bob in the form of an arc. You will see that. I have seen that. There is a continuous, constant conversion of restoring force to 0 to maximum and so on. And the property of inertia that is responsible for the particle to shoot from its mean position towards the other side. So it keeps continuing the oscillatory motion over the length of time. The medium is surrounded by, if the medium is free from any other resistive forces or the air or oil, etc. If it is free from any other medium, then the particle or the bob may swing indefinitely over the length of time, because it is continuously converting potential to kinetic, kinetic to potential, continuously going like that. So, in order to satisfy the conservation of energy, the bob is kept oscillating continuously without being damped. If there is a medium surrounding, is a damp or is a kind of damping nature, if there is any damping medium is surrounding the particle, oscillator particle, you cannot expect the bob to oscillate indefinitely. Okay. See, I have given one more diagram example here. Look at this here, the spring. It is moving up and down. Okay. Here, this spring is moving up and down here. See that here? It's moving up and down because of the restoring forces. So, the moment of simple harmonic motion, as I already told you, it can be represented by a sinusoidal wave, as in this diagram. Okay. Coming to the characteristics of a simple harmonic motion, I told you that it is a periodic and oscillatory. There is the swinging of a spring, this one. See, this is, look at this diagram. So, this is a simple harmonic motion and it is represented by sinusoidal wave. F is the F is equal to minus k. Let's look at this diagram. There one red one and the blue markings. The blue represents the position of the this swing, this particle. You see now this maximum, and the x is meaning the other side, it goes to the maximum, but the restoring force is working in the opposite direction. Okay. When displaced from its mean position, the restoring force tends the body to vibrate to and fro about the mean position. And we have seen that in the previous discussion, the restoring force is directly proportional to the displacement. And it requires the concept of inertia to overshoot at the mean position.